Mathematical expectation, sometimes I'll call it expected value, but it's a way for us to understand how much money the player will win or lose each time they play the game, or how much money the dealer is expected to win or lose each time somebody plays the game. Now, if you're creating a game, like you will be starting on Friday, do you want to make money off of your game, or do you want to lose money off of your game? You're going to want to make money off of your game, which what is important to understand here, I'm not teaching you how to gamble. I'm teaching you how gambling is set up. It's set up for you to lose. It's set up for the dealer to make money. That's how casinos make money, okay? So I'd like to teach you the math behind that, okay? So every game has a mathematical expectation. If I step up to play this game, I am expected to either win this much every time I play, or I'm expected to lose this much every time I play. Okay, and that's what mathematical expectation is. So what you're going to do with mathematical expectation is you're going to draw, oh wow, I thought I did this already. Okay, you're going to draw that little chart that you see in your notes. Okay. You basically need to figure out the probability for each situation and how much, I'm going to say money, when we make our games it's going to be Tootsie Rolls, okay? But how much money are we expected to win or lose in that given situation, okay? So that's what this value is, okay? I've taught you how to find the probabilities, and what we're going to do is we're going to have to find the probabilities of any scenario of a game, and then we're going to attach a value to it. There's a 1 in 6 chance that I'm going to make $1, so that value would be +1. There's a 5 in 6 chance I'm going to lose $1, so that value would be -1, okay? And then what we're going to do to actually calculate the expected value of the game is we are going to take the probability times the value for each scenario and add them together. Okay? So what I'm asking you to do is for any game, I'm going to ask you for the probabilities, but for the probabilities of each situation. Okay? So go ahead and read through example 1, this roulette situation here. So just like with any other probability situation, you have to think about the sample space in order to be able to set up your probabilities. All right? So our sample space, what is it? Our ball could land on red, black, or green. Now, those aren't equally as likely, okay? We don't have just 3 different situations. How many reds do we have? 18. We have 18 red. We have how many black? 18 black, and we have 2 green. So how many, are they called slots? How many slots do we have total? 38. So we have 38 slots in our sample space. Okay? The probability of winning, what do we need to win? What kind of, okay, red. We need red to win. How many reds are there? So we have an 18 out of, what did we say, 38? 38 chance of winning. Probability of losing. We lose if what happens?
It's not.
It's not red. And how many are not red? 20 out of 38. Okay. So now the probability distribution is just that chart that I told you about. Okay. We need to write out the value of each probability. Okay. So how much money are we betting here? We're betting $1, correct? If we win, we gain $1. Do you agree? So we have a probability 18 out of 38 to win. And if we win, we are up $1. We have a 20 out of 38 chance to lose. And if we lose, what happens? We're down $1. Okay. So, if we want to talk about the mathematical expectation, and you'll see that I'll call it like E, okay? If we talk about the mathematical expectation or the expected value, those two are interchangeable. What we're going to do is we're going to take the value times the probability for each scenario, value times probability, and then we're going to add all of those products together. Okay. If we do that, what do we get?
-2.
Okay. -2 out of 38. Okay. Now, I have been describing all of this as me playing the game, right? So this would be the mathematical expectation for the player. Can you give that to me as a decimal?
-0.0526.
Thank you. Okay? Every time I play the game, I am expected to lose 5 cents. That's what that is saying. Okay? Now, obviously, if I play it one time, it is not physically possible for me to just lose 5 cents, right? It's either I gain $1 or lose $1. But that is what I am expected to lose each time I play the game, which means if you played the game 100 times, how much money could you expect to lose? If I lose, how'd you get that, Nick? Okay, whatever our expected value is, so our expected value was -2 over 38 or 0.0526. If we multiply that by 100, we get -5.26. So if I play this game 100 times, I can expect to lose $5.26. What's happening to the dealer? If somebody plays their game 100 times, what can they expect to happen? They're going to make $5.26. Okay? If you were creating a game, is that an expected value that you would want as a dealer? Are you okay with making only $5 every 100 times somebody plays? Okay. Some of you might want that because it's more appealing to the player, right? Ooh, a 5 cent loss each time I play, that's not really big, right? That might be appealing to a player, but that might not be appealing as a dealer. See what I mean there?
We're going to see that you might as well make it pay $100 per spin.
Okay. All right. Why do I keep talking about what you might like? Okay. This is eventually building up to you creating a game and you figuring out the expected value of your game, and then we're actually going to play each other's game and see if the data matches what we had set up in our probabilities. Okay. That's where this is going. Isn't that exciting? I'm excited. Okay, please take a few moments as I erase to read through example 2. Okay, some of you are already writing down your sample space. What is our sample space?
1, 5, 10, 20.
How many ones do we have?
6.
How many fives? We have 2 $5 envelopes and 1 $10 envelope, 1 $20 envelope. Okay. Now, when I say what's the probability of winning and what's the probability of losing, that's going to look a little different than what we're actually going to put here in number 4. Yes?
Do we need to write it out like that, or can we do it like we did for the example 1?
You can do it that way, yeah. Since this was a smaller number, I felt like I could write it all out. But if you say $1 times 6, I can live with that. Okay, save some room, right? Okay. What is the probability of winning? How many different ways can we win? There's actually 2 different ways to make money, right? We can draw the $10 bill or we can draw the $20 bill. So right here, I'm going to say, well, technically there's a 2 out of 10 chance of winning. Okay. How many ways are there for you to lose money? 6 out of 10. Now, Mrs. Holman, that doesn't add up to 1. That's okay. It is possible to break even in this game. You're not winning and you're not losing. Okay. Now, when we create this probability distribution, value I'm not going to slow it all out. I ran out of room. Okay. We're actually not going to put just those 2 numbers. Okay. Yes, we are going to put 6 out of 10. And how much money are we losing if we draw the $1 envelope? We're actually losing $4. Okay. What else could happen? We could also draw one of these $5 envelopes. Okay. How much money are we making or losing? Okay, we're not, right? Our value would be 0, and there's 2 out of 10 of those envelopes. Now, yes, there are 2 different ways to win, but we're going to separate those out. There's a 1 out of 10 chance that we draw that $10 bill, and if that's the case, how much money are we making? We're making $5. And then there's a 1 out of 10 chance that we're going to draw the $20 bill. And how much money would we be up then? 15. That sounds quite nice, doesn't it? Okay. Now, here's something that is important to consider in your probability distribution. since we are considering all the possibilities of the game, what should these numbers here add up to be? They should add up to be 1. Your probabilities in your probability distribution should always add up to be 1. Okay. All right, so some of you are already calculating away. The expected value for the player, we're going to take -4 times 6/10 plus 0 times 2/10 plus +5 times 1/10 plus +15 times 1/10. How much money is the player expected to win or lose each time they play the game? Positive or negative? Each time a player plays this game, they can expect to lose 40 cents. Okay? What does that mean? If the player played the game 100 times, what do we do with that number? Okay, we're going to take the expected value and we're going to multiply by 100. Okay? The player can expect to lose $40 if they play the game 100 times. Okay? Now that kind of stinks, doesn't it? However, think about this. If you were the dealer and this was your game, if somebody played, and a variety of people played your game 100 times, how much money are you making? You're making $40 for every 100 times your game is played. That's what that means. Each time your game is played, you are making 40 cents. Okay? So if the player has a negative mathematical expectation, then the dealer would have what kind of a mathematical expectation? Positive. Okay? And it's the same number, just opposite. Okay? If the player has negative 40 cents for mathematical expectation, then the dealer has positive 40 cents for mathematical expectation. Okay? Now, what would it mean if our mathematical expectation were to be 0? What? Okay, if our mathematical expectation is 0, then both the dealer and the player, they're just breaking even. Okay, some of you may want that for the game that you create. I don't know. Okay, these are things to think about. All right. Okay. So what I have for you, and it was supposed to actually go on the back side of that worksheet, but we had a little miscommunication with the copy machine. I have 5 games on this sheet of paper here. And what I want you to do is do like we did here, figure out the sample space, probability of winning, probability of losing, mathematical expectation, and then how much we're winning or losing for 100 games. So it's going to look very similar to your notes, okay? In addition, you're going to, when you have all 5 of the games, which games are fair? Fair games. What do you think that would mean? Okay, so what would your mathematical expectation be? 0. You'd have mathematical expectation of 0. Okay. Which ones are the best games to play? Which ones are the worst games to play? And then you're going to decide which games you would want to play versus what you would not want to play, and tell me why. Okay. These are all things I want you to think about in preparation for you actually creating your own game for other people to play. Okay. So this is your homework, these 5 games. We do have 10 minutes left. So I would like you to get through at least one of these games before you leave. Okay, now, I do want to point something out about this worksheet, okay? Like the low, lower, lowest, it says the payoff is equal to the amount wagered. So what I would like you to do is just always assume that we're gonna bet $1. It's just gonna be easier. And so, like in low, lower, lowest, the payoff is equal to the amount wagered. So if you lose $1. If you win, you gain $1. So you get your dollar back and they pay you what you bet. Does that make sense? Okay. I just want that to be clear. Okay, go. You're going to want to do this on a separate sheet of paper, or you can do it on the back since they didn't get copied correctly. Like if you want to do it on the back of your notes, you can do that.
Alright, so what are we doing?